All right, let's jump right in. We have all seen the absolute explosion of these incredible AI-generated images, right? The tech just seems to get more and more complex every single day. But what if I told you the latest, biggest breakthrough came from making things simpler, like radically simpler? Today, we're going to break down a paper that flips all that conventional wisdom right on its head.
I mean, just look at this image. It's really hard to believe a computer made that. For years, the road to getting images this good involved building bigger, more complicated models. They relied on other pre-trained systems, complex loss functions, which are basically just fancy ways for the AI to grade its own homework, and all sorts of clever but messy engineering. The core belief was that to get a clean image out of digital noise, the AI had to become an expert on the noise itself.
And that really brings us to the heart of the matter today. What if focusing on the noise, on the static, was the wrong path all along? What if the real secret is to just ignore it and focus on the picture you want to see? Now, to really get why this is such a game changer, we first have to understand the old way of doing things. For a long time, the gold standard for these models was something called epsilon prediction. Don't worry about the Greek letter epsilon. Epsilon just stands for noise. So instead of training a model to look at a fuzzy image and guess the clean one, researchers actually got better results by training it to predict the exact pattern of static that was added to it. It's kind of like trying to restore a dusty old painting by perfectly describing every single speck of dust and then hoping that when you subtract all that dust, you're left with a masterpiece. It's a bit backward, right? And here's the crucial problem with that whole approach. Predicting random noise is incredibly hard for a computer. Think about it. A clean image has structure. It has rules. It has patterns. A face has two eyes, a nose, a mouth. But random noise, by its very definition, it's unstructured. So asking a neural network to model pure chaos across millions of pixels, well, that's a huge and maybe totally unnecessary job. Okay, this is where things get really cool. A classic idea for machine learning comes into play and just completely changes our perspective. It's called the manifold hypothesis, and it gives us this beautiful way to visualize what's actually going on. So picture this. Imagine the space of every possible combination of pixels is a gigantic empty room, just a vast three-dimensional space. The manifold hypothesis says that all the natural images, photos of cats, trees, people, they don't just float around randomly everywhere in that room. Nope, they all lie on a very, very thin, intricate surface. Think of it like a single, delicate thread twisting and turning through the immensity of that room.
And this is the key insight. This is the aha moment. A clean, real image has a very specific location. It's on that thread. But the random noise we add to it, that noise can be anywhere in the room, totally off the thread. So when we ask a model to predict the noise, we're forcing it to search the entire vast, high-dimensional room. That is a really, really hard search.
A super simple experiment makes this crystal clear. On the left here, you see a basic 2D spiral. That's our manifold. That's our thread. The researchers then kind of hid this simple spiral in a much higher dimensional space and asked a noise prediction model to go find it. And as you can see on the right, as the dimensionality of that room gets bigger and bigger, the model gets completely lost. It just falls apart, producing nothing but a random cloud of points.
And this right here brilliantly illustrates the solution. On the left, you see that failure of noise prediction again. It's totally lost. But on the right, that's what happens when you have a model that was just asked to predict the original spiral, the clean data itself. It works perfectly. It doesn't get lost searching the whole room. It just learns how to find its way back to the thread. So this insight leads to a pretty radical simplification. If predicting noise is the big problem, then the solution is, well, it's almost laughably obvious. Just stop doing it.
Yup, that's it. Instead of predicting epsilon, the noise, the model is trained to predict X, the clean image. This is the original, most intuitive idea of denoising that the field actually moved away from years ago. It's a full circle moment, a return to first principles, but this time we're armed with a new understanding of why it's the right way to go all along.
And the results? Oh man, the results are just staggering. This table shows a common score for image quality where lower is better. Using the exact same model, the new X prediction method scores a fantastic 8.62. Another method, V prediction, gets a 9.6. And the old standard, our friend epsilon prediction, it completely fails with a score over 370. This isn't just a little bit better, it's a totally different class of performance.
So you might be thinking, what kind of incredibly complex next-generation model do you need to take advantage of such a simple idea? Well, that's the best part. You don't. Let's talk about the model they built, which they call Just Image Transformers, or JIT. The whole philosophy here is just pure minimalism. JIT is a totally standard, off-the-shelf vision transformer. It doesn't need some special tool to compress images into a latent space. It doesn't need any extra rules or guiding losses to tell it what a good image looks like. It works directly on raw pixels, and it's completely self-contained. It's really just a transformer, doing one simple job: predict the clean image. This slide really puts it all into perspective. The old way, on the left, it's like this fragile tower built out of a bunch of different parts. You need multiple other AI systems that are already trained. The JIT approach on the right just sweeps all of that away. It's clean, it's elegant, it learns everything it needs from scratch, straight from the pixels. And get this, it does all this while handling incredibly high-dimensional data. For a standard image, JIT breaks it into little patches, and each one of those patches is a vector with 3,072 dimensions. Remember that toy experiment? For a noise prediction model, that high number of dimensions would be absolutely catastrophic, but for X prediction, it's no problem at all.
So why does all of this matter beyond just making better AI art? Because this isn't just about a new technique. It's really a whole new philosophy for how we should build these kinds of generative models.
This quote from the paper just summarizes the whole shift perfectly. We've been asking our neural networks to do this incredibly hard and maybe wasteful job of modeling total randomness. This research argues that we should respect the network's limited brainpower and focus it on the thing that actually matters: modeling the beautiful, structured data of our world.
And because this approach is so simple and self-contained, it's not just for images. This basic diffusion plus transformer recipe could be applied to any kind of complex scientific data where making a special compression tool is really hard or even impossible. Think about things like protein structures, molecular data, or complex weather patterns. Which leaves us with this final thought to chew on. In a field that always seems to be in this relentless race toward more and more complexity, maybe the most profound breakthroughs actually come from taking a step back, questioning our basic assumptions, and rediscovering the incredible, surprising power of just keeping things simple.